All right, this is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate. Please don't share contact information during class for your own security reasons. All right, so here we go. We have our brain stretch today, a bunch of different questions that you can answer. So hopefully this one we definitely know from yesterday. In order for there to be work, the force and displacement must be what? Parallel or perpendicular? And then down here, a question about power. If two motors lift the same object the same distance, meaning they're doing the same thing, the same work, which one is more powerful? The slower one, the faster one, or are they the same? And then a couple of easy math problems here. So what's the work done on a 20 Newton box that's pushed 5 meters along the ground? So remember, work equals force times distance. What's the power then if that box is pushed in 4 seconds versus if that box is pushed in 10 seconds? So it's the same box for all three of these problems, but you're going to use the work up here and then divide it by the time down here. And same thing, use the work that you calculate up here and divide it by the time down here. Awesome. All right, let's go ahead and start going over some of these answers. I do see that we are working hard on these. So in order for there to be work, force and displacement must be parallel. Remember, we talked about if we lift an object, our force goes up and the object goes up, and therefore work is being done. But if I already have an object in my hands and I'm just walking around horizontally, that is not parallel, and therefore there's actually no work being done, which is sad because it takes a lot of effort. But mathematically, physics, there's no work being done. So they do have to be parallel, right, like this to each other. Okay, if two motors lift the same object the same distance, that means that they're doing the same work because force and distance are the same, but the more powerful one is going to be the one that does it faster in less time. All right, we took a look over here then at some of our equations. Work equals force times distance. So we should be able to annotate this, right? The force is in newtons, so the 20 newtons is our force. The distance is in meters, so 5 meters is our distance. So plugging that in, no worries. Thank you for letting me know, Micaiah. So plugging that in, right, we can see somebody put their work up here, equals 20 times 5, which gives us 100 joules. And I love that you included the units, joules for work, absolutely. All right, so that being said, we then took those 100 joules and we're going to go ahead and figure out which person is more powerful. Now, already knowing this idea of the slow versus fast motor, which person should be more powerful? The person who does it in 4 seconds or the person who does it in 10 seconds? Tell me in the chat box. Just theoretically, based on what you already know, who should be more powerful? The 4-second or 10-second person? Yeah, absolutely, because the 4-second person is faster. Right? So remember, we've already talked about the faster you are, the more powerful you are. So to prove that to ourselves, we can take that 100 joules of work that we calculated up here, right? So here's our 100 joules of work that we calculated up here. Plug that in, divide it by the time. So the first person did it in 4 seconds. 100 divided by 4 equals 25. However, I do want to remind you that the units for power are actually watts. So power equals 25 watts. Smiley faces if that makes sense. Smiley faces if that makes sense. So power equals 25 watts. Awesome. Thank you, Nichelle. Thank you, Landon. Now, if we do the same thing over here, again, it's the same exact power, it's the same exact work. So power equals 100 joules again, but this time divided by 10 seconds. And we already have an answer here. Someone wrote 10, and that is true. 10 divided by 10 will give, 100 divided by 10 will give us 10 watts. So again, we proved to ourselves that the faster you are, the more power you have. The fast person has 25 watts. The slow person only has 10. Excellent job. So this was a review from yesterday. Hopefully you feel pretty comfortable with this because it's going to inform how we understand what we're doing today as well. So make sure you open your attendance check. Make sure you give me a green check. Start of class word is under the link. I have 12 green checks so far, 24 of you. So I have about 50% participation, always aiming for a little bit more. Looking good. Let's get green checks, please. Thank you, Alexis. Let's get one from Ari and Brandon, Danny, Estella, Jelly, and Travis, green checks. And let's keep going. All right, so there are only 18 days left of the quarter, and when do classes end? Tell me in the chat box, when do classes end? If there are only 18 days left of the quarter, when do classes end? Tell me in the chat box. Yeah, so they end in those 18 days. Remember that courses end on October 28th at 11:59 p.m., so 1 minute before midnight. So remember, classes end at the end of the quarter. They're only quarter-long classes. So you only have 18 days left to get caught up on anything that's missing or to redo anything that you haven't done well on, okay? So today we are talking about simple machines. There is a support session today at 1 p.m. Yes, at 1 p.m. if you need help on any of your past assignments. Tomorrow we'll have an exam over the Unit 5 and 6, over Units 5 and 6. And then Friday we start already Unit 7. Remember, there are only 9 units, so we're actually almost done with all of our information before our final exam. All right, go ahead, give me a thumbs up, everyone, if all of this makes sense. Thumbs down if we're confused about anything here. Thank you, Nichelle. Thumbs up, everyone. Thank you, Hannah. Thank you, Kimberly. Perfect. Thank you, David. All right. So taking a look here, I just want to show you the calendar here. So today is the 2nd, right? So we're right here on the 2nd. And you can see the last day, again, is going to be in yellow here. So the quarter ends on the 28th. Again, it ends 1 minute before midnight. So you have until 11:59 p.m. to get everything done. And remember, classes are only a quarter long, so they will be ending on the 28th. You will have the 29th and the 30th off. Those are teacher days, but not student days. And then quarter 2 will be starting on the 31st, which I know is sad because that's actually Halloween. So if you celebrate that, sorry, you still have school on that day. All right, so let's take a look here. We've been talking all about work, and the ability to do work. Today we're going to take a look at simple machines and the factors that influence force. And we'll also talk about pulleys and levers today. So lots of interesting stuff. So we should be able to identify and describe the 6 types of simple machines. We should know what a fulcrum in a lever is. We should be able to divide and calculate mechanical advantage and explain how simple machines can either increase or decrease it. I know, it's so sad, Ari. Yes, school often started on the day of my birthday when I was a kid, so I feel your pain. Feel your pain. And here's our agenda for today. Really, your birthday is on Halloween? Do you celebrate Halloween? If so, I'm sure that's lots of fun. All right, so we are talking about, we are completing, you always wanted to send school. I know, it is kind of sad if your birthday isn't during school because then nobody's there to celebrate it at school. Yeah, summer birthdays. But at least you don't have school during the summer, right? All right, so let's go ahead and open up our 6B notes. All right, going to send those out to you. Give me a green check if those are working for you, red X's if you're having any issues. Remember, you want that open by the time we get to question number 1. I will be giving you all of the answers word for word throughout the lesson. Oh, were you, David? When were you actually born, though? All right, I have 7 green checks so far out of 25. Looks like I don't have any red X's, so I'm assuming it's working for everyone. So keep on opening that up or be ready to take pictures. Oh, on the 27th. So close. You were just too excited. Yeah, Aqua, 1 second. I was just sending out the notes. I didn't want to confuse people. All right, here we go. So today we are talking about, you're supposed to be born on July 4th. That's cool. All right, so today we are talking about, that means you would have gotten a bunch of fireworks. When were you actually born, Michelle? All right, sorry. So today we're talking about all these different types of simple machines. Let's go ahead and jump into those. July 10th, so you were a little late. So let's talk about this. Why do people use machines? You can either type on the board or type in the chat box. Tell me, why do you think people use machines? What's the purpose of machines? Yes, absolutely. To make life easier. Any other reasons why people might use machines? To make humans more fat. So to allow us to be lazier might be what I think you're getting at, Aqua. Any other reasons that we might use machines? Right, so get things done faster, I think is what you're trying to say, right, Nichelle? Get things done faster. Yeah, to help us. Absolutely. And there are a lot of machines that can do amazing things that humans just can't do by themselves, right? So if you think about so today we're going to be talking a lot about simple machines. And so simple machines aren't necessarily like the electronic machines that you think about, but simple machines helped ancient humans do amazing things like build pyramids, for example, which would definitely be very hard to do if we were just lifting things by ourselves. We're not that strong, right? Okay, so let's go ahead. Again, you can type on the board or type in the chat box and I'll put it up there. What's the purpose of a ramp? I have a picture of a ramp right here. What do you think the purpose of a ramp is? Yeah, so this might allow wheelchairs to access a building. Yes, to help, absolutely. What other things might you use a ramp for? Get things with wheels upstairs, to go up or down. Yeah, I often think about when I'm like moving boxes, right? It's a lot easier to push a box up a ramp than to have to walk up the stairs with it, right? Yeah, skateboarding to roll up heavy objects, absolutely. Good. All right. So that's awesome. Ramps are actually going to be a type of simple machine that we're going to be talking about. Again, they're not actually electronic machines, but they are machines that make our lives easier. Yep, take heavier objects up easier because you don't have to apply as much energy. Absolutely. What about wheels? What is the purpose of a wheel? What is the purpose of a wheel? To get around places, yes. For entertainment, yes. Machines can be used for entertainment. That's true. What other things might you use a wheel for? I see Jorge typing. I see Nichelle typing. I see Landon on the board. Yeah, so we might use them for things like cars, right? What else? If you can't carry anything heavy, you could just push it, right? So we could use wheels on things like carts, which allow us to carry heavy objects. Yeah, dollies, exactly. Dollies help us carry heavy objects. Awesome. So I think you guys are getting the sense here that this helps us lift things, right? What about levers? Take a look. We have a seesaw over here, which is an example of a lever. What do you guys think levers might be used for? Hopefully you're getting the idea here, right? We see up here, Landon, looks like you're putting TVs, radios, computers, phones for fun, right? So a seesaw might be used for fun, but what is the seesaw actually doing? What is the seesaw actually doing? I know, Flintstone style car having to pedal. I remember doing that when I was a kid in like those plastic kind of cars that you could pedal around. You could actually do that with, there's like the pedal boats. Have you heard of those? Where I grew up, there was a lake where they had the pedaling boats where you could pedal and it would actually make you go, yeah. All right, so let's go ahead and jump into this. I think we're getting the idea that simple machines make our lives easier, okay? So here we go. What a simple machine is, though, simple machine means it's simple. So it actually only needs a single or one force in order to work. So for example, when we use a ramp, which is a type of simple machine, that's called an inclined plane, the force that we use is just a single force to push a load up that ramp or up that inclined plane. All right, thumbs up if that makes sense. Thumbs up if that makes sense. All right, awesome. All right, so there are 6 types. We're going to be talking about the 6 types. So the first 2 are an inclined plane, right, which is a slanted surface, much like the ramp that we discussed in our brainstorm. And a wedge, for example, is actually 2 inclined planes back to back, and this can actually be used for separating something. So a wedge, like an axe, can be used in order to separate the sides of a log away from each other. But again, there's only actually a single force. The single force comes from the axe or the wedge, and then that can actually change into 2 separate forces that split the wood apart. Okay, but again, initially there's only a single force. All right, go ahead and fill in the blank for number 1 with the word single. All right, you have 30 seconds to do that or take a picture. Ready, set, go. I need green checks from everybody. Good, good, good. All right, waiting on a green check from Alicia, Ari, Danny, Jarrett, Landon, Shelby, Susan. Remember, again, if I'm not seeing lots of participation as we're going through class, I'll go ahead and move you to check in with you in a different room. So make sure that you are participating and following along with us. All right, again, Ari, Danny, waiting on Estella, and Shelby and Susan. Green checks, please. Green checks, please. Shelby, Susan, Estella, Danya, and Ari. All right, let's go ahead and keep on moving here. All right, so the other types of simple machines, there are 4 more, right? Total of 6. So one of them is the screw. Okay, so a screw is an inclined plane that encircles a central rod. And most of you are probably familiar with what a woodworking screw looks like, but there are actually other forms of screws that we will be talking about. But again, what's happening here is we use a single force, right? So you might use a single twisting force, and that allows you to have some rotational force that can bring things together or make it easier to keep things together, okay? A lever, on the other hand, is an arm. Arm just means like anything. So it could be a board, it could be a rod, it could be a wheelbarrow. So an arm that pivots on a point called the fulcrum. So the fulcrum is the point at which it pivots. Thumbs up if that makes sense. We're going to talk about that word a number of times. So thumbs up if that makes sense. All right, a wheel and an axle. All right, so a wheel is going to, you probably already know what a wheel is, but the axle is the actual post through the center of a wheel. So you actually need both of these in order for it to be considered a simple machine. So you can see the wheel and the axle through the center of it. And then a pulley is when we have a rope or a chain that actually gets wrapped around a wheel. So you can notice that some of these simple machines actually get incorporated into the other simple machines. But again, as long as it only requires one input force, it's still considered its own simple machine. So a pulley allows us to lift things by pulling on a rope that's wrapped around a wheel. How many of you have ever seen one of these? Yes or no? Tell me in the chat box. How many of you have ever seen a pulley? Right? Yeah, awesome. All right, so let's go ahead and make sure we understand the brief definitions of these. Right, we've got wedge, lever, screw, wheel and axle, inclined plane, pulley. Use your whiteboard tools, use the line tool, match these up to their definitions. Right, which one is a slanted surface? Which one's an inclined plane that encircles a central rod? Which one is 2 inclined planes back to back used for separating? A wheel with a post through its center? A rope that's wrapped around a wheel, and an arm that pivots around a fulcrum. Go ahead, get your answers up there. Let's get lots of participation, please. Checking on my participants. I see Nichelle on the board, Chris on the board, Micaiah on the board. Thank you. Brandon. Awesome. Keep working up there. I see Antonio and Landon participating. David M. Hannah. Excellent. Keep on working up there. Kimberly's on the board. Jorge's on the board. Lorelai's on the board. Looking good. All right, I'm going to pause your tools in about 5 seconds, and we're going to clean this up, and this will be number 2 in your notes. So get ready to do number 2 in your notes. All right, pausing those tools. Oh no, Alicia. I know, the lines sometimes just show up very suddenly, depending on how fast your computer is. All right, let me go ahead and grab my red marker here, and let's match these up. So a wedge, yes, is when we have 2 back-to-back inclined planes that are used for separating, much like an axe, right? Or a knife or scissors, all right? A lever, on the other hand, is an arm that pivots on a fulcrum, much like a seesaw. Let me change colors here just to make sure it's nice and clear. A screw is an inclined plane that encircles a central rod, right? We have those threads around a screw. A wheel and axle is a wheel with a post through its center. It was hard to define it without using the word wheel, so hopefully that one was pretty obvious. And then an inclined plane is a slanted surface that we might push an object up. And a pulley is when we have a rope wrapped around a wheel as well. All right, so this is number 2. I'm going to go ahead and actually give you 60 seconds because this is a little bit longer. Green checks when we have this one saved or you've taken a picture. About 5 seconds left. Have about half of my green checks. All right, let's get some green checks, please, from Asia, Elena, Alicia, Ari. Let's see here. Lorelai, Micaiah. Green checks, everyone. And we're moving on. All right, so let's go ahead. We're going to go over a couple of these a little bit more in depth, just because some of them are a little bit harder to understand. So a screw, again, we talked about, is an inclined plane that gets wrapped around or encircles a central rod. No, not for extra credit, Ari. You need to... So woodworking screws are probably the one that you're most familiar with, so things like this up here. And so you can see that there's the inclined plane that gets wrapped around, all right? But often at the edge, we also have a wedge. Okay, I sent them in the chat box, Ari, so you should be able to open them from the chat box. Okay, and I can double check Yeah, I don't know why they wouldn't be showing up on your plan, but make sure that you refresh it and then open up the notes from the chat box. Okay? And basically what a screw does is it uses rotational force in order to make work easier. So think about if you were trying to keep two pieces of wood together, all right, with a nail, all right, oftentimes with a nail, you have to do a lot of force, a lot of hammering in order to get that nail to keep the pieces of wood together. And then at that point, it's not always even the best because sometimes the nail will actually separate and the wood pieces will come apart. Smiley faces if that makes sense. If you've ever done any woodworking or you've ever seen it, right, nails themselves aren't always the best option because they don't actually keep the pieces of wood together the best. So instead, what happens here is by using a screw allows us to have a lot more force that keeps those pieces of wood together by rotating, okay? However, a lot of times it does take longer, all right, in order to do this work, right? Hammering a nail takes a lot of force over a short amount of time, whereas a screw, right, we have to do that twisting over and over again in order to get it to keep things together. But again, sometimes it's worth it, right? It makes it easier to do as well as increasing the amount of force that keeps wood together. What we can see here is that when the threads are closer on something, again, it makes it take a little bit longer, but it actually makes it easier. So the closer the threads are, the easier it is for something to have that rotational force. Okay, what are some other examples of screws that you see up here on the board? What are some other examples of screws that you see up here? Some of these you might not have realized were examples of screws, but go ahead, tell me in the chat box. Yeah, absolutely. A slide, one of the screw slides, right? The ones that wrap around. Those are examples of screws, which makes sense, right? Because if you were to fall from that distance, right, or try to lift something up that distance, that would take a lot of energy. But a slide or a screw allows us to get down from that height much easier, or to go back up much easier if you've ever climbed up one of those slides. Yeah, a gumball machine, you can see an example of a screw there. What else do we see? Yeah, so for example, when you throw a baseball, right, there's a screwball that's an example of that. Yes, that might be more for an advantage over the person being unable to predict what you're doing, though. This right here up here is what's called an auger. It allows you to drill holes in the ice using a screw. Again, it's very hard to just kind of hammer through ice. So an auger takes longer, but it's easier because you're able to use that rotational force. Give me a thumbs up, everyone, if this is beginning to make sense. Again, simple machines make our lives easier. Sometimes they take longer, though, to do things. Awesome. All right. So for example, this is what's called Archimedes screw. I'm going to go ahead and show you a video, and I want you to go ahead and tell me, what do you observe is happening in this video? So let me pause this. All right. Sorry, guys. It seems like it's not working on the screen. So go ahead, open it up in the chat box and tell me if it works that way. That didn't work either. Okay, let me go ahead and share this with you. I don't know why that's not working. All right, let's go ahead and take a look at this. All right, so observe what's happening. All right, tell me in the chat box, what do you see happening in this video? Either you clicked on the link or you watched it on my screen. I know my screen lags a little bit, but hopefully you were able to see a little bit of what was happening. Tell me in the chat box, what did you observe? I can play it again. Yes, excellent. I see an answer from Nichelle. I see Chris typing. We can see water starting down here at the bottom. And then as the guy is moving the screw, what's happening? I see Kim typing. Make sure, even if you have the same answer as someone else, still tell me in the chat box so you can reinforce your own learning. Yes, exactly, Kim. There we go. Looking good. All right, so this is what's called Archimedes screws. So this is actually really cool. This is actually used still even today. This was invented thousands of years ago, but we still actually use the same concept in many of our machines today. So Archimedes screw, or Archimedes water pump, can be used in order to bring water from a lower area up to a higher area. Remember, if we were to do this by hand, that would require us to take buckets and buckets and go back and forth, walking up and down. And so that would take a lot of effort. But Archimedes screw, by using a simple machine, the screw, this actually makes it much easier, right? So what we can see here is that as the screw turns, it actually lifts the water up to a higher location. Give me a thumbs up if that makes sense. So this is making this hard work much easier. Okay, so Archimedes, he was a Greek mathematician, physicist, engineer, inventor, astronomer. He lived 287 to 212 BC. So this means BC means like before Christ, right? So this was over 2,000 years ago, right? So over 2,200 years ago. So a long time ago. And Archimedes' screw was invented around 250 BC. All right, so this was a very long time ago, but again, simple machines have been around for a very long time and been helping us do a lot of difficult tasks. Okay? All right, so talking about a wedge, remember a wedge is two inclined planes back to back, and one force actually becomes two forces that can separate or cut something. So you can see that right here. Again, we start with a single force, and as it goes in, those wedges, those inclined planes, actually change the direction of the force. So that allows us to separate something. All right, give me a green check if that makes sense. Green check if that makes sense, keeping you on your toes here. Green check if you understand. So we're changing, this is a simple machine that changes the direction of force. And we use these wedges all the time. So anytime you think about something that can cut something, like an axe or a knife, right? Those are all examples of wedges, but there are also other uses, right? We use a wedge to keep a door open. You can see a wedge at the edge of the pizza cutter, as well as being combined with other simple machines like the wheel and axle and a lever as well. Okay, so that being said, talking about levers, levers are, again, when an arm, which could be a bar, a stick, or a board, many different things, an arm rotates or pivots around a point called the fulcrum, right? So the fulcrum is the point at which a lever rotates. And changing the position of a fulcrum actually changes the type of effort force that you need on that lever in order to do work. So essentially what we're doing is we're making things easier to lift by applying a force over a distance, okay? So let's think about this. If you were to try to open a door, all right, a really heavy door, do you think that you would do you think it would be easier to open the door from the handle or from the hinges? Tell me in the chat box. If we're trying to open a door, I can go ahead and show this right here. Right, so if here's my door, right, here's the handle and here's the hinges. Where do you think it would be easier? Should I push closer to the hinges or closer to the handle? Yeah, definitely closer to the handle. So the further away you are from the pivot point, the fulcrum, the easier it actually becomes, right? So the more distance away from the fulcrum, or the pivot, the easier it is to do. All right, so you can see here some examples of levers, right? So this one right here is a pretty familiar one. This is like a seesaw where the fulcrum's in the center, but that might be if you were to use a hammer to remove a screw. If we were to use pliers, right? You put the effort on the end, the fulcrum's in the center, and the part that you're using, the lever, the load is at the edge, right? The class 2 lever is something like a wheelbarrow. So the pivot point is at the wheel, and you put your force at the end with the load or the object in the center. And something like this one, a class 3, would be like tweezers or tongs, where the fulcrum's at the end, you put the force in the center, and what you're picking up is at the end. Give me a thumbs up if this is beginning to make sense. All right, so there are many different types, but as long as there's a pivot point or a fulcrum, we know that it is a type of lever. Awesome. All right, go ahead, fill in the blank for number 3 with the word fulcrum. You have 30 seconds. Ready, set, go. All right, waiting on green checks from Asia, Alicia, Antonio, Ari, David M. Green checks, please, Jarrett and Susan. Again, Asia, hello. Antonio, Ari, green checks, please. Susan, green checks. Let me know if you need help, but I do need your green checks. Asia, Antonio, Ari, green checks, please. Filling in the blank with the word fulcrum. Thank you, Ari. Asia, waiting on you. Looking good. Let's keep on moving here, everyone. Okay, so let's go ahead and let me actually show you again how a lever works. So again, the longer the distance you are from the fulcrum, the easier it is to do something. So let me go ahead and share this with you on the board. All right, and you can actually also open this up yourself if you would like to play around with it. Okay, so I'll put this in the chat box as well. All right, but we're going to go ahead and do the balance lab. So we're going to go ahead and click on the balance lab. All right, and what we're going to do is we're going to put a really heavy thing on one side. All right, so I'm going to go ahead and put a heavy object kind of in the center on the right. Okay, and then I'm going to go ahead and put a smaller object on the other side. Okay, so let's put this kid on the other side. Now, what you can see here is, is that initially, the heavier guy is definitely winning. Thumbs up if you guys can see that. Thumbs up if you can see that. I know it might be a little bit laggy, but what you can see is the one with the heavier person is definitely winning. However, the further I begin to move this kid away from the center, okay, you can eventually see that he actually, sorry, I should actually make this guy a little bit closer. The further away that this kid actually gets, the easier it actually becomes for him to balance him off. So again, you can see that even though he has a very small force, by increasing the distance away from the fulcrum, he actually makes it easier to lift this really heavy object. All right, give me a thumbs up if that's beginning to make sense. All right, I can show you a different one. All right, so let's say I have this lady right here. Okay, and this girl right here. So again, when she's close to the fulcrum, she's losing, but eventually as she goes further and further away, she can actually win. Right? So the further away you are from the fulcrum, the easier it becomes to lift a heavy object. Okay? So what does that all mean? This is what is called, sorry. Okay, I'll come back to that. No, I'm going to skip this. So this is what is called mechanical advantage. So levers and pulleys actually increase mechanical advantage, and mechanical advantage is how easy it is to do work. All right. So more mechanical advantage means it's easier. So here's what's happening. When we have a small input force, like that little kid trying to lift something over a really long distance, what this means is that on the opposite side, on the opposite side, a large output force on a shorter distance can actually be lifted. Okay, so what's actually happening here is on both sides of a lever or a pulley, on both sides, the amount of force, the amount of work is actually exactly the same. But on one side, it feels easier because we're able to use less force. All right, so let's take a look over here. So remember, work equals force times distance. So let's say we're trying to lift this object 2 meters. And the object weighs 25 newtons. Okay, so let's multiply those together. What's the work that is done on the right side? Tell me in the chat box. What is 25 times 2? All right, so we've got work equals 25 times 2. Yeah, so this is going to be 50 joules of work. 50 joules of work. And on the other side, it's actually going to be the same work. So it's still 50 joules of work on the other side. However, now we can figure out what's the input force needed, right? So in this case, 50 joules is our work, which equals the force, which we're trying to solve. So 50 equals force times the 5 meters, which is the distance, okay? So let's go ahead and try to solve this. In order to get the force, we need to do the opposite of whatever's next to it. So what's the opposite of multiplying by 5? In the chat box, everyone, what's the opposite of multiplying by 5, or the inverse? Yeah, we're going to divide. So we're going to divide by 5, which will get rid of this. But whatever I do to one side, I also need to do where? Whatever I do to one side, I also need to do where? On the other side. So I'm also going to divide by 5 on the other side. So what is 50 divided by 5? So what is 50 then divided by 5? Yes, so the force that we would need, our input force, is actually only 10 newtons. So take a look here. Just by this person being further away from the pulley with a larger distance, they actually have to use less force. And what do you think? Is that going to be easier or harder? Yeah, physical science has a lot of math. We definitely actually don't use that as much math as we might in other classes. This is way easier, right? So again, a bigger distance on one side means that we can have a smaller force, which makes it easier. Okay, so that is mechanical advantage. So what a pulley does is it increases mechanical advantage by making it easier for us. Okay, now sometimes we can actually decrease mechanical advantage and make it harder for us. And why might we want to make it harder for us? A lot of times we don't, right? We want to be lazy and make it easier. But the reason we might want to make mechanical advantage harder is to increase speed. So for example, a bike uses many simple machines in order to change force to speed. So take a look here. We've got our pedals, okay? And we have our wheel back here, okay? Thumbs up if you can see that. Okay, so pedals at the front, wheel in the back. Okay, so what's actually happening here is when you pedal, right? Imagine when you first begin pedaling a bike, sometimes you even have to stand up because it's so hard to start pedaling a bike, right? So you have to put in a really large force. But are your feet moving very far from each other? Tell me in the chat box. Yeah, we might need to get stronger. But are the petals actually moving very far? Okay, so we are putting in a huge force, but are the petals moving very far from each other? Yes or no? No. So we've got a really large force over a very small distance. Those petals don't move far. But what's happening is at the back, because they're connected to each other, at the back, what happens is we end up with these gears. And so gears take that and they turn it into a small force. But anytime you turn it into a small force, then the opposite's going to happen. So the small force means that now the wheel begins to move over a very large distance. Give me a thumbs up if that makes sense. So a large force becomes a small force, which means that a small distance becomes a large distance. And so the larger the distance of that bike, of that wheel, means that you get to go faster and faster and faster. So if you've ever seen the gears on your bike, what you'll notice is that the one with the smallest gear is actually your fastest gear. Give me a smiley face if that makes sense. So your smallest gear is actually your fastest gear. This is how you can race really, really fast, right? Because again, the smaller the force back here, the larger the distance that the bike can actually go. Awesome. All right. So again, in summary, there are some different things that we can do. We can increase mechanical advantage to make things easier for us, right? Take a small force over a big distance, like in a pulley or a lever, which allows us to pick something up that has a big force over a small distance. Okay, lift heavy objects. Or we can decrease mechanical advantage. So this makes it harder for us, right? Because we have to input a really big force over a small distance, like the pedals. But what happens is this allows a small force to be distributed over a big distance, giving you a lot more speed on a bike using the gears of a bike. All right, so again, we could do either depending on what we want. So for number 4, fill in the blank with the word harder. And then we just have one last one that's really quick. Green checks, please. Go, go, go. I know we're out of time. All right, looking good. Green checks, please. I have 14, which is about 50% of you. Perfect. All right, awesome. Let's go ahead and do this last one. So let's go ahead and work on this together. So if we want to lift an object that has a big output force, so a heavy, heavy object, that is a small distance away from the fulcrum on a lever. So basically, this is the red side. Okay, what would we need on the opposite side? Tell me in the chat box. On the opposite side, are we going to use a small force over a big distance or a big force over a big distance? Tell me in the chat box. Think about it. Remember, they need to be opposites. So a big output force becomes what type of input force, and a small distance becomes a big distance. Yeah, so we actually want a small input force. Right, so we're actually going to use a small input force. And if we're using a small input force, do you think that's going to make it easier or harder for us? So over here, we can see a big distance, small input. Whereas on the other side, we have a small distance. Yeah, this is actually going to make it easier for us, right? If we have the smaller input force, that makes it much easier for us, right? Smaller forces are easier for us to use. So that's going to make it easier for us. And remember how easy something is mechanical advantage. So are we decreasing or increasing mechanical advantage? Tell me in the chat box. Are we increasing or decreasing mechanical advantage? Yeah, we're increasing it. Awesome. All right, so for number 5, the answer for number 5 should be small, easier, increasing. All right, go ahead, answer number 5. You have 30 seconds to give me a green check, and then I will give you your last word. Go, go, go. All right, I have 22 green checks, still missing, I think, 6 of them? Green checks, please. Looking good. Awesome. All right, everyone. So we talked about simple machines, fulcrums, mechanical advantage, and what increasing or decreasing it does for us. Tell me, how are we feeling? Point on the board for me. How are we feeling about these different objectives for today? You have your whiteboard tools. Point on the board. Awesome. Feeling pretty good. Looking good. Some of us feeling awesome. Still need some help. No worries. Make sure you're coming to support sessions if you need help. Looking good. All right, everyone. So make sure that you get your 6B notes submitted. And then here we go. I'm going to stop our recording.